Bom, pessoal, boa tarde a todos. Em nome do Departamento de Física e da coordenação do nosso programa de pós-graduação, eu queria dar boas-vindas. Eu sou Remo Ruffini, dizer que é um prazer, né, tê-lo aqui. E para falar, dizer, né, com mais alguns detalhes, né, a história, né, científica do professor Ruffini, eu gostaria de convidar o nosso ex-professor, né, professor Hélio Coelho.
Nossa, já fiquei assustado, porque eu não vou falar. Eu acho que ele é que vai falar sobre toda a história da organização, mas é um prazer apresentar o professor Remo Ruffini, e para mim também é uma coisa maravilhosa, porque trabalhar ou viver desse tipo de ambiente acadêmico, se eu tivesse de voltar, o que eu gostaria de ser de novo seria físico e trabalhar em universidade. Não existe coisa melhor. Toda hora está falando italiano, português, espanhol, inglês, tudo que é coisa. É uma experiência muito boa para o pessoal que está fazendo pós-graduação, né? E claro que o professor Ruffini será a pessoa que vai apresentar com detalhe o que é que ele faz, qual a razão da vinda aqui. Mas eu gostaria talvez de fazer um resumo, principalmente por um fato que ocorreu com minha fase de doutorado nos Estados Unidos. O professor Remo Ruffini é professor na Universidade de Roma e é o presidente dessa organização que assinou esse acordo hoje com a Universidade Federal de Pernambuco, o ICRANet, que ele vai explicar tudo direitinho para vocês. E um fato importante é que ele, juntamente com o professor John Wheeler, foram os descobridores, teoricamente, dos buracos negros. Eu era estudante na Universidade da Pensilvânia, quando, na época, o fato era uma celeuma, a mesma coisa como o modelo padrão nos dias de hoje, né? A partícula Deus e coisas desse tipo. E aí foi anunciado que existiria esse colóquio. O negócio foi tão surpreendente que tiveram de fazer no teatro da universidade, para 3.000 pessoas. E eu participei desse tipo de colóquio, me lembro perfeitamente do professor Wheeler falando sobre isso, e eu creio que o professor Ruffini era um estudante, já era professor na Universidade de Princeton, perto da Universidade da Pensilvânia, e foi uma coisa surpreendente. Então a pessoa está ligada a isso, questão das estrelas de nêutrons e uma série de fatos fundamentais dentro da física, de acordo com o que vocês vão verificar.
Só um lembrete, talvez vale a pena mencionar que o professor John Wheeler foi o orientador do Feynman, né?
Sim, o professor Wheeler, cara, era um homem do nível de prêmio Nobel e foi orientador do professor do Feynman, né, o famoso Feynman. Então, estamos tendo hoje aqui a presença de uma pessoa importantíssima nessa área da física. Eu não gostaria de me alongar mais, porque o professor Ruffini será a pessoa que vai apresentar toda a história. Grazie.
Grazie. I have a few languages, but not yet Portuguese. Therefore, I will speak either in Italian or in English, but maybe it's better at this stage to speak English as well. But I will be very happy to. I would like first to show a few pictures quickly about ICRANet. And ICRANet was something which started first as ICRA at the University of Rome, founded by Riccardo Giacconi and Abdul Salam, before they got the prize in physics. And Riccardo Giacconi, myself, Francis Everett, and the director of the Specola Vaticana, who were very closely related. And after 20 years that ICRA was operating, we decided to make one step in advance and invent an international organization. The members were Stanford University, the University of Arizona in Tucson, and ICRA, and the state of Italy. This is the law which was passed unanimously by the Italian government, and Armenia and the Vatican. And this was all the organization, this international organization is made like CERN in the sense that has extraterritoriality and all the privilege and immunities for the members of the organization. This is our headquarters in Pescara, and you are very welcome. In front there is also, for the reason I will tell you in a moment, in addition to the Italian and the Vatican and Armenia, also the Brazilian flag. And here is the library, the lecture rooms, and also on the ground floor we found some interesting structure, maybe dating long time in the past. Therefore, this is the headquarters in Pescara. We have another seat at the Sapienza in Rome, which is, as you know, one of the oldest universities. And here again, we have the place to work. And there is this room, which is a very special room. And because everybody coming, maybe we will do also, if we will have an office here, the same thing. We ask the distinguished scientists to sign the wall. And it's like that when John Wheeler came, signed the universe, taking conscience of the universe, and when Riccardo Giacomo came, he said, yes, but instead of looking with the eye, if you look with the X-ray detector, you will see much farther in the universe. And then there were many other people who signed this wall, including the Deutsch and all the rest. But the interesting thing is that many of the people who signed the wall, in one case after 2 weeks, in some case after few months, they took the Nobel Prize. So we proceeded. This was the case of Tuft, that he came and then after 2 weeks he got the Nobel Prize. And here are the graduate student offices. The other structure, which is of the ICRANet, is the State of the Vatican. This is the beautiful location of the Vatican Observatory near Rome, in Castel Gandolfo, and this is the Vatican Observatory in Tucson. And then there is the activity at Rio de Janeiro. Last night we had the pleasure to have the dinner with Sergio Rezende, and there is this very historical letter. When Sergio was president, he conveyed to me in Rome the request by President Lula to have Brazil joining ICRANet, and Sergio was the one who put the signature on this first step, and now Brazil is definitely a member of ICRANet. At the moment we have a seat at CBPF, but we have also some dream, which I will tell you passing. By far the most interesting action was the agreement in Brazil, the agreement between CAPES and ICRANet, which I signed with George Guimarães. And since then, what we have is a very, very intense exchange in which a student can come to our PhD program and visitor professor can come to teach in our ICRANet seat. Therefore, now that we have signed the agreement this morning, certainly some of our professors will be able to come here, and vice versa. Some of your professors and students come to the campus in all the seats of ICRANet. We have also with FAPERGE an agreement I hope very much to have also an agreement. And then this is not yet a reality, it's a dream, this one. The dream is that there has been a place in Rio that is called Casino da Urca. Now, if you take a book of astrophysics, of astronomy, of astrophysics, there are chapters devoted to the Urca process. And the reason that the name Urca process, because the idea of the Urca process came to Gamov and to Professor Schoenberg. At the time, he was not professor, he was student of Gamov, with a Guggenheim Fellowship, if I understand correctly, and was between Mario Schoenberg and the work on the concept of neutrino and the cooling of neutrino, the Urca process was born. I have a dream to have the headquarters for all the activity of ICRANet in Brazil at the Casino da Urca. We are discussing that with the mayor, but if you have sympathy for this idea, please make your voice heard, because this, I think, it will be a fantastic way of celebrating one of the greatest ideas ever had by the human being, which happened exactly at Urca. And therefore, in addition to Rome, Rio, Pescara, which we have already said, there is this other seat in Armenia, and then the new baby is this seat that we are going to inaugurate shortly at the university at Nice. We are acting in different places. This is already old, because we have, since 2 days ago, also here, Florianopolis, we have made collaboration with 10 universities, and we have students all over coming from, one of the students also, Gabriel, from here working with us. Here is the description of Nice, an old villa of the 17th century, which we have redone. We will soon inaugurate with the student. This is our seat in Yerevan. Very quickly, this is the president of the Armenian Academy. I presume you have also here in Brazil an Armenian community, which must be as usual very high level, a lot in Argentina, but I'm sure also here. And then we look for new members. One of the things we did a lot of, we are active in creating schools, but the structure which we are more eager and which is the essential part of the ICRANet activity, teaching and research, has been this program of graduate school, in which we have the University of Rome, the University of Ferrara, one of the oldest universities in the world, the University of Nice, Grenoble, and university in Germany, including now Bremen and Oldenburg, and we deliver a joint degree in relativistic astrophysics. Namely, the students who have the PhD obtain the diploma and they are registered in all the universities. The hope is to extend this 6 member institution also to Brazil. And we are thinking to bring to 3 universities from Brazil and 2 Mexican join our global PhD. Now this is the symbol of ICRANet, and that's as I was telling you earlier. How do you see a black hole? The black hole is here. It's a curved black hole. Here you have 5 particles, 1, 2, 3, 4, 5. You let them go, and instead of being in an ellipse, they form this beautiful Möbius bottle-like, and we decided to take this as the symbol of ICRANet, of the particle rotating around the curved black hole. Okay, so much for the scientific research topic. We are growing, and now all of these are practically PhD theses which are ongoing in ICRANet. Maybe I will start now, if there are no questions, leave that introduction in ICRANet and go to the astrophysics. I have two presentations, one shorter, one longer. Maybe I sit on this one, and if we need, we go to, this okay?
It's okay?
Yes, if it's needed, we go to the, if we need more details, we go to the other one, okay? I would like at least to say a few words about two different concepts. There is a choke already. One is a supernova. Another concept gamma ray bursts. This is a different concept. I will try to say in a few words something about what is this object and what is that object. They are completely different conceptually. And then I will go to the thing which excites most the situation today. A supernova, if you have to choose one object which has been most successful in the history of humankind, you have to choose this object, this supernova, which exploded in 1054, observed by the Chinese, the Japanese, and the Korean astronomers. This is one of the latest pictures taken by the Hubble Space Telescope of this fantastic object that still today is expanding at 700 kilometers per second. And the origin of this object in 1054 came from this object over here, which exploded, and the material kept expanding from 1054 up to today. Of course, one of the topics to explain a supernova was the work of Oppenheimer and Volkoff and his school, who studied the concept of a neutron star. And the essential point was the one of Mario Schoenberg working with George Gamow at work. Namely, what they understood is that when the star, prior to be a supernova gravitationally collapse, it becomes tremendously hot, but the last bit in order to collapse and to cool is the neutrino emission. The crab expands. The neutrino are certainly emitted, but although every day the crab makes something new, even last week there was a flare observed, there are still open issues on the crab nebula. We don't yet understand, certainly the reason of the collapse is the one given by Gamow and Schoenberg, but we do not yet understand the bounds which allow from the neutron star the expansion. Therefore, it's fantastic that although has been observed since 1054 and Messier and this thing goes on, there are still open issues and observation. But the key point is that this dim object at the center of the crab was discovered in 1967 to rotate with a period of 33 milliseconds, and instead of having a continuous luminosity, this object was turning on and off 33 times a second, therefore implying that it was rotating to be very condensed. This was the fantastic discovery of the neutron star in 1967. I was at the time, Elio mentioned, in Princeton, little younger, without a beard, and this was John Wheeler. John Wheeler, the way you met him in 1971. And at this moment, Wheeler said, Remo, let's not work on neutron star because there will be many people working on, too many people working on neutron star. And around Wheeler, we were not more than 10 people. Then there was another group of Wheeler had been the teacher of Feynman. Therefore, we enjoyed some time to have discussion with him. And I don't want to open this point because otherwise we'll give another talk. But once let's not. I went to see him, but let's not talk on that. It was very exciting, unpredictable, Feynman. But also unpredictable was and very exciting was Wheeler. But Wheeler said, let's move on. Everybody will go neutron star. Let's move on further and look to another object which is even more extreme than a neutron star, is a black hole. And we wrote this article introducing the black hole in '71, and this is the picture that a German artist made. And the black hole was no good for the supernova. Well, the supernova is clear what it is, a supernova. It's the formation of a neutron star. The black hole is more extreme, is even more compact. And what to do with the black hole? Because you cannot see it in principle, you were mentioning. But there was a fantastic student who came from Greece in those days, I think it was 68, 69, Dimitris Christodoulou. And Dimitris was at the year when he arrived in Princeton, he was 16. He had left an high school in Greece where he was fighting with the teachers. Wheeler went to Paris, spoke to him, and in Princeton you could admit a student even without bureaucracy, even if he had no degree. If the professor at Princeton likes to have a student, a guarantee, he can bring the student in. Therefore, he brought Dimitris. I was a very young professor, 24, and he said, well, you are a young professor, this is a young student, 16. Go on. And after 1 year, Dimitris passed the undergraduate. Boom. After another year, he passed the general exam, 18. And then finally we spent 1 year to work on the thesis. The thesis had two aspects. One about the black hole with me, and another one with John Wheeler. Well, I don't want to tell all the story of this, but let me tell you that Dimitris got the thesis that he worked with me. He finished last year in a volume of 700 pages, the part of the thesis given by John Wheeler. And then he said, fortunately, I solved the first part and he took his PhD, but the second part he just finished last year. And anyway, this is a nice picture with John Wheeler in the middle, myself, and later, and Dimitrios. And this is an historical place. It's the office that used to be of Einstein. And if you go to Princeton, you can still visit this place. Nobody emphasized, but it's a very nice place because there was a fireplace. And Einstein wrote with the chalk, Herrgott, raffiniert ist Herrgott, aber Bosapher ist nicht. Lord God is refined, but is not malicious. And we took this picture in front, but the key point is the thesis with Demetrius pointed out that the black hole has a mass, a reducible mass, a Coulomb energy, and a rotational energy, like a particle. Therefore, this was the idea with Wheeler, to look at this object not as a mathematical object, but as a physical entity. And this physical entity has a formula. And this formula tells you that if you are in order to be regular, this inequality has to be fulfilled. And if you fulfill this inequality, the message of this formula is that in principle, you can extract from a black hole 50% of the mass energy. This was the incredible message. Because if you have a mass of material, baryons, in the star, like in the sun, you can take 1% of energy during the billion years of the life of the sun. But the message with the thesis of Demetrius was that in principle, you could take in the formation of the black hole 50% of the mass energy, much, much more. This was the incredible message. And I started to work since then on that problem. And we tried to extract energy by magnetic field. We even invented a machine like a tokamak. These certainly work very well for, works extremely well for extracting the rotational and the electromagnetic energy from the black hole in very large black hole in active galactic nuclei, but was not the point I was interested in. I was interested in something in which 50% of the energy could be extracted in the process of collapse. Okay, this stopped. I have other slides, and for now, let's start with this other topic. I hope you got to the supernova. Let's go to gamma ray burst. What is a gamma ray burst? This is a gamma ray burst. And it's a fantastic story. How they were discovered. The discovery, I have other picture if you like to see, but I don't want to spend, though I enjoy telling the story, but I don't want to spend too much time on that one. The point is that there was a special man in Soviet Union who was extremely intelligent, but also extremely bizarre. This was Zeldovich. Yakov Borisovich Zeldovich, the man who made the atomic bomb, the H bomb in the Soviet Union. And Zeldovich was also the founder of the astrophysics group in Moscow. Therefore, there was a group around Wheeler in Princeton, a group in England around Stephen Wheat. In England, there was no person like Wheeler or Zeldovich. It was a group of young people, Martin Rees and Stephen Hawking and so forth, but small. And then there was a group around Zeldovich. But Zeldovich was incredible. Zeldovich wanted always to show absolutely that the Soviet system was winning. This was his fixed idea. Therefore, when this is a beautiful story. When Gamov introduced the concept of the hot Big Bang, but Gamov had left Soviet Union and and was in the West, Zeldovich did a paper proving that the beginning of the universe had to be cold, not hot. And he made a theorem just to show how stupid was this man who escaped from Soviet Union. But it's very interesting that many years later I met him, and I had the pleasure to talk with him. And then I asked him, I said, but how did you, was ideology, why you did that? Well, he said, I had to prove, but let's be frank, he said. It is clear, because he will never give up, it is clear that Gamow has been one of the greatest Soviet astrophysicists. Therefore, no matter after the discovery, you know, give up. Soviet astrophysicist. Well, anyway, but Zeldovich presented a crazy idea that he wanted to show that the Russian could arrive to the moon first. And therefore he decided, since he had done the A bomb and the H bomb, to put an H with a rocket, an H bomb on the moon. And said at a given time, everybody look, and the Russian arrived, the Soviet. Absolutely crazy. Of course, this was not accepted even in Soviet Union. But the point was that the idea was proposed. The idea was proposed. Therefore, immediately, or no, after a few years, the United States put the Vela satellite between the Earth and the Moon and make sure that nuclear bomb will not explode either on the Earth because there was the non-proliferation treatment, but also on the Moon. And these detectors were omnidirectional. I mean, they were not, the reason of having 4 active at every moment is that from on board of each satellite, though they were very large direction, you could pick up at the time of arrival and reconstruct the place where the bomb would explode. And after, we don't know for how long they observed, but it was clear that they start to observe phenomena which look precisely like lasting of the order of seconds, 5 seconds, 6 seconds, in 1, 2, and 3 satellites, but they were not coming from the Earth, fortunately. Maybe one of them came from the Earth. They were not coming from the Moon. They were not coming from the planetary system, not from Mars, not from... And then the mystery started, where they come from. They were publicly announced in '71, and we made a meeting in San Francisco, in '74. We made a meeting in San Francisco with Cherngosky, and finally we disclosed this object to the community. Gamma ray burst. Mystery, where they come from. Okay, I was dreaming about my mass formula with Christodoulou, and with a young student, a young collaborator, who now has become a member of the French Academy and so forth, Thibaut Damour, we hypothesized that the origin of this GRB was a black hole at the moment of formation. But nobody knew how far they were. And this paper is still today very beautiful. It was a theoretical paper showing that if you have heavy ion collision, you can polarize the vacuum if Z is larger than 137. And like that, around a black hole, you could have vacuum polarization a la Euler-Heisenberg. And if you have an overcritical black hole, you will create electron-positron plasma, and this should be the origin of GRBs. But the incredible part of the prediction was that if this model would have been correct, then gamma ray burst, we predicted, should have an energy of 10 to the 54 erg. 10 to the 54 erg is something that nobody had imagined before, because the energy of the sun is 10 to the 33, the number of stars in the galaxy is 10 to the 12, therefore if you take the energy of all the stars in the galaxy, 10 to the 12 that gives 10 to the 45. In order to reach 10 to the 54, you will need 10 to the 9 galaxies. Therefore, all the galaxies in the universe from that single object. And therefore, we stopped. We did not go on. Here is a nice picture of the time. Jim Wilson, myself, and Thibaut Damour. And then we waited. We waited until a big saga started, in which from the Villa satellite to the Compton satellite was launched. They were discovered short GRB, long GRB. It was discovered that the GRB were democratic. They were distributed in all directions and in all the energy over the universe, but there was no clue how far they were coming from. And the reason was that the angle of these detectors would allow still to have many optical objects, stars, in the direction of view. And then this Italian-Dutch satellite, Beppo-Sachs, was launched, and here we have Paolo Giommi, which I think you were working already.
That picture I did it.
You did?
That picture you see there, I did it with my hand.
Okay. Therefore, we are starting to touch real time here. This is the picture done by Paolo of this satellite.
Not the satellite, the GRB there.
Of that one?
Yeah, the blue one.
This one?
Yes.
Well, this has been one of the most important discoveries ever.
I did the software, I did that picture.
Now you understand why
And
we
Costa
put his first name. But you were in the team of this, and you did actually
I
the
did
data
the analysis.
analysis.
That picture was
Fantastic. That is one of the most important pictures ever, because it gave the position, Paolo, with very, using, do I say correctly, using the X-ray wide field detector and the narrow field detector, it was possible to locate accurately enough the position of a gamma ray burst. But what was more important that, and now we are going on, okay, let me finish this because I want to go on to more actual things. It was discovered that the gamma ray burst, instead of lasting just 6 seconds, they were presenting a prolonged emission, and this prolonged emission allowed finally to locate much better, and now we have all these satellites working, and from all these satellites it was possible to locate the position in the sky and open the large collaboration with the optical and the VLT, and this is the action of today, and the result of this is that indeed gamma ray bursts have an energy of the order of 10 to the 54. Because they are not, there were thousands of models, if they were comets, if they were nearby and so on. Finally it came out 10 to the 54. Okay. I hope you got to the point. This object has the energy of all the stars in the universe during the flash. Now let's go to the, okay, we studied the black holes, how to this plasma comes out. We have even used the knowledge of some classical people from Moscow working with Zeldovich on the heavy nuclei, and finally the model has become quite sophisticated. These are the two eras. Supernova on one side forming neutron star, black holes forming gamma ray burst. Fantastic. But this one is one object, this one is a different object. The astrophysics is completely different. But then something fantastic happened. That with this discovery of in 1904-25, a gamma ray burst appeared to temporally coincide with the supernova. What is the reason why a neutron star forming a supernova can coincide with a gamma ray burst which is created by the black hole? This was one of the most dramatic moments, and finally we are understanding, thanks to Orge, to many of the students in Rome, that the gamma ray bursts are much more complex system. It's true that they last of the order of seconds, but they represent something. The fact that there is a supernova and a gamma ray burst coinciding in time, it means that there is something profoundly new in astrophysics. And the general idea was developed about this new concept, the induced gravitational collapse sequence. The first point which has been essential is that if you look at all massive stars in the sky, of the order of 120 solar masses, for example, Eta Carinae, they are in binary system. And for example, Eta Carinae has a period of 5.5 years. And the more massive star evolves much faster than the less massive star. And if it evolves faster, it forms through a supernova a neutron star. Indeed, the system formed not of massive star, but evolving by evolution with a neutron star and a companion star. They are extremely well known. They are called binary X-ray sources. And therefore, it was clear that a system, a massive system, very massive system of two stars evolves to a binary X-ray sources. The next step has been to go one step further. And this is a nice set of pictures that we developed with Orge. The fact that if you have two massive stars, therefore the more massive star evolves from a supernova, the less massive star keep evolving. And then here you have what I showed before, a neutron star together with a neutron star here, together with this star, which start to evolve itself. And if this star evolves and goes to become a supernova, if the neutron star is very close by to this star undergoing supernova, what can happen? Something very dramatic, that the mass of the supernova is secreted on the neutron star, and the neutron star gravitationally collapse and form a black hole and emit a gamma ray burst. Therefore, from a single, this is the sequence, namely that you have a core and a neutron star binaries. It goes a supernova, the matter of the supernova crit on the neutron star, form a black hole, and then you have a gamma ray burst. These are the formula written by Orge, and system of this kind have been for the first time observed from the Fermi, the Swift satellite, Agile, Suzaku, and all the other. There has been one case in which the a gamma ray burst very, very energetic, 2.8 10 to the 53 Earth, very close by 0.5 at a redshift of 0.54 could be observed at the same time by all these X-ray telescopes, and they look from the ground with the optical telescope and locate the object, locate the energetic, and the new thing has been the analysis of this 200-second emission. The system emit this in for 200 seconds. There is a first event A second event B, and a third event C. And in this 200 seconds, there is a completely new physics ongoing on this system, namely the explosion of the onset of the supernova, the accretion of matter into the neutron star, then the formation of the black hole with the gamma ray burst, and then a third phase, which is by far the most interesting. Therefore, this has been practically the new approach of this gamma ray burst analysis, which previously were examined globally, and instead here there has been an analysis in time, very, very accurate, of the spectrum, of the radius involved, with the temperature emission, and it was clear that this object is just the accretion of the supernova onto a neutron star. Then the second event, the B event here, is the typical GRB emission when the black hole is formed. I don't want to give you more detail, but we can infer the energy of the GRB, the baryon loading, the Lorentz gamma factor, the density of matter around. And then there is a third part, which is the one on which we are working currently, in which there is this part C, in which the luminosity in the X-ray has a very, very special value, which decreases in time extremely regularly. And this episode 3 is the clue of the work that we are doing in these days in the induced gravitational collapse. And I would like, before closing, give you an idea why we are so interested in this last episode 3. And then, of course, after 15 days, you have the supernova observation. Well, the new picture which comes out of this analysis is that you have a binary system formed by a star undergoing a supernova here, and then accreting on the companion neutron star. The companion neutron star forms a black hole, it emits a gamma ray burst, and from the initial neutron star and the companion supernova, you get out a black hole and a new neutron star. This is the space-time diagram of this behavior. And this is something completely new in astrophysics. Let me try to explain why so incredible. When Fermi introduced beta decay, I enjoy always reading that. I'm writing a book on Fermi. And the discussion between Fermi and his collaborator was, yes, we understand you had a neutron. The neutron decay in a proton, electron, and neutrino. But where the proton comes from, where the electron comes from, where the neutrino goes, what? And the beta theory was so beautiful because it explained that you can have transition, and then all this was formalized in the S matrix of this, for example, in E plus, E minus. Now, particle physicists knew that all the time, that you can create mu plus, mu minus out of E plus, mu minus with S matrix. That is okay. But in astronomy, this is new. namely that you have an object. An astronomer likes to look at an object, physical object, lasting forever. I mean, like the crab, you look after 1 century still there, and you make the spectrum. And here we have a phenomenon lasting 200 seconds. And in this 200 seconds, you have a stellar core undergoing a supernova with a companion neutron star, and this object forms a black hole and another neutron star coming out. This is a completely unheard process in astrophysics. And it's necessary, really, to have the collaboration and the interest of all theoretical physics and experimental physicists to introduce this style of looking at the data of a fraction of a millisecond, not for hours, and in every fraction of a millisecond to find some new physics. And at this stage, therefore, what we are looking is a new system with gamma ray burst. And I always am fascinated thinking about that if you take the birth of the solar system 5 billion years, this gamma ray burst comes from 13 billion years away, some of them, 12 billion years away, much, much earlier when the solar system was practically born. And they are so far in space and time that the light travels for billions of years, even before the birth of the solar system. And while this signal from the gamma ray burst approach after 7 or 8 billion years, the solar system was initiating, and then it went on. You have the dinosaur, you have Pythagoras, you have the invention of the telescope by Galileo, and this gamma ray burst is still approaching, entering the galaxies. And then you have the V2, you have the rockets, you have Giacconi, you have the VLT telescope being developed in Chile, and finally the gamma ray burst arrives with this message, and you can understand what the origin of this gamma ray burst is. Therefore, for the first time, we are really obtaining the observation from the farthest part of the universe, and we are exploring the region very near to the initial Big Bang. Therefore, this is a little bit to explain why we are so excited about relativistic astrophysics. The first 50 years of Einstein theory were interesting for mathematicians, with the only exception of the Sobral observation of the bending of light. There were very few data purporting the application of general relativity. General relativity was almost dying at the end of life of Einstein, because there were no observational data. Mathematics was becoming tremendously difficult, and very likely general relativity without people like Lifshitz, Landau, who were convinced that it was worth it to continue and write the beautiful book to survive, general relativity will have finished. Then something dramatic happened. I think it's interesting. I always do the analogy. General relativity was a little bit like Chinese. Why? Chinese would have been disappeared some 20 years ago because it was too difficult to write. Then the computer came in, and then the Chinese started to write on the computer, and the Chinese language had a revival, and now is irregular. General relativity was the computer coming in. Again, the survival of general relativity, because the computation, which when I was a student we used to do by hand, the computer can't do that. and therefore was relevant. But the important point was the Crab Nebula and the pulsar and the neutron star and the black holes. That suddenly, in the last 50 years, things have completely changed. And this is the reason why at the next meeting, maybe we show the poster of the Grossman, we want to celebrate this very drastic change with the general relativity. The first 50 years, a tragedy for observation and no astrophysics result. With the general relativity coming, with the relativistic astrophysics coming in, general relativity has become the backbone of the entire field, and tests on the binary gravitational waves got the Nobel Prize and all details, and finally the field has become of great maturity. And this is the reason why at the Grossman meeting next year in July, and I hope many of you will participate, we will celebrate not only the 100 years of general relativity, not only the year of light, where processes like GRB, creating pair out of the vacuum, come out, but we would like to celebrate the 50th, the golden jubilee of relativistic astrophysics. I've been discussing with Itamarati that the members of ICRANet, the state member of ICRANet, namely Brazil, Italy, Armenia, and the State of the Vatican, propose to the United Nations next year a celebration of this event, that ICRANet be among the sponsors of this idea. And in that sense, since this morning, finally, we signed the agreement with your university, you will be able to foster and participating with us to this event.
Perguntas?
There will be a possibility to have something here in Brazil for this kind of.
Excuse me?
There will be any possibility to have a meeting here also?
Yes, I think we are preparing. I will give you a few of these posters. And you see Brazil is in pole position, but we would like to have some satellite meetings. And we are thinking next year to have 2 satellite meetings in Brazil. We have to decide now. We have been working to this association of different universities from Brazil, and we are planning very much to have 2 satellite meetings to the Grossman meeting in Brazil.
While the supernova is a bit symmetric, generally the gamma ray burst is there is a preferential axis, yes? Preferential, the axis of rotation? Generally?
I presented this the short version. That needs the longest version. But it would be too long to go to that one, but let me just go to the, well, maybe you can put a moment. The key point is, at the beginning, the gamma ray burst was conceived as a single phenomenon. And, questo è l'altro?
Sì.
No, vai oltre. Okay, here. No, prima. Yes, was a single phenomenon, the one that you have a collapse and jets. This was the beginning. The system is clear that is much, much more interesting and rich. And I did not show you some of these slides, but it is extremely is much more interesting. While the initial part of the gamma ray burst are different from burst to burst, there is a last part which is very, very regular. And this implies that there is no jet as such in the X-ray, and there is no jet, but they are more spherically symmetric. And then there is an high energy part instead, which has a jet structure. Therefore, is much more.
So the symmetrical one is not the gamma ray, just the X-ray. Yes.
Okay, you got to the point.
I was just wondering. So maybe sometimes you measure a supernova, but you cannot measure the gamma ray burst because the X is not aligned with the Earth.
The X-ray are always symmetric. Now,
But they are energetic enough for detection?
yes, but the key point is that when you have a binary, this is the major result done by Orke. If the neutron star is close enough, then you have accretion and you have formation of black hole and you have a gamma ray burst. But if the neutron star is not close enough, what happens is that the accretion is not large enough and you have just a supernova. You have only the first part. Therefore, up to now it was not clear that there are two families of GRB. The one less energetic, in which you don't have any big structure, and the one more energetic, in which you have the black hole formation and all the high energy structure. Much more rich than what was taught before. And still in the 200-second.
Any other question? Well, if not, let's thanks, Professor.
Bene, poi
Você não coloca aqui, não deu uma
Where?
Você trabalha na CBPF?
Thank you very much.
This is just a certificate. No, this is for you. Just to prove that you present.
Well, we are in contact with Kepler a lot. And we keep in touch with Kepler.
Tudo tem a ver, mas tem a ver. Você entende muito bem essa área e é